Kia ora koutou katoa. Really nice to see you here at Te Whare Wanaka Araki, Lincoln University. Um, if you've not been here before, welcome to the university. We're really proud of the changes that have occurred. For those of you who have been here but may have graduated a while ago, a lot of the buildings are slightly different than you might have remembered. As Katie indicated, I'm the provost here at Lincoln University. It gives me great pleasure to welcome you to this discussion. This series is delivered in partnership with the Bioeconomy Science Institute. Together, we aim to create a space where science, industry, policy, and community can come together to explore the future of Aotearoa and New Zealand's land-based ecosystem. The purpose of the series is simple but vital: connecting research with real-world challenges and highlighting the collaborations needed to support sustainable land use and resilient production systems across New Zealand. Today's session focuses on one of the most pressing challenges facing agriculture and the bioeconomy: reducing nitrous oxide emissions. These gases sit at the center of conversations about climate action, farm performance, and the future of sustainable farming. Meeting our national climate targets while maintaining productive and profitable farming systems will require innovation, collaboration, and practical solutions that actually work on the ground. This event will explore the latest research tools and on-farm approaches aimed at reducing emissions across agricultural landscapes and how science is being translated into real-world impact. We're very fortunate to be joined by two outstanding researchers. First, Tim Clough, Professor of Soil Science at Lincoln University, whose research focuses on nitrogen and carbon cycling in grazed pasture systems. His work uses stable isotope science to better understand the processes behind greenhouse gas emissions and to develop practical mitigation strategies that can be applied on farms. Joining him is Dr. Steve Thomas, Principal Scientist and Team Leader at the Bioeconomy Science Institute. Steve brings a strong applied perspective, working across collaborative projects that evaluate land use options and innovations to reduce greenhouse gas emissions and improve water quality while supporting resilient farming systems. Together, they will share insights into the science, innovation, and partnerships shaping the future of low-emission New Zealand. It promises to be a highly informative and thought-provoking session. So the format will be, each speaker will give a little bit of introduction, a talk, you know, Tim, hour and a half, something like that, right? And then we'll have a suite of moderated questions and then open it up to the audience. We do have a hard finish at about 2:15. So apologies for that, but tea and coffee will be available after. So welcome to the stage, Tim Clough.
Thanks for that introduction, Chad, and thanks for the opportunity to speak to you today. So my understanding of proceedings is I'll do about 15 minutes and I'm going to sort of cover some basics, and Steve's going to come in and talk about some potential mitigation solutions and what makes a key mitigation solution and what we may or may not know. So when we think about nitrous oxide being produced in the soil, we're really talking about microbial processes that are going on in the soil. And one of the key ones that gets everything going is nitrification. And you will have heard terms like nitrification inhibitors, biological nitrification inhibition, and these processes, these inhibitors, inhibition, they're honing in on this nitrification pathway. And we start with ammonia here, or ammonium, moving through to nitrate. Lots of intermediary steps we're not going to talk about here, but each step is driven by an enzyme. And enzymes depend on things. They have optimum pH, optimum temperature, and in this case, the very first step here, ammonia oxidation or ammonia monooxygenase, requires oxygen. So it's an aerobic process. If we have anaerobic conditions, it's not going to happen. But generally in our pasture systems, nitrification will kick off. We've got a pasture pH somewhere around 6. That's pretty optimal for nitrifiers. And in our pasture systems, work by Hong D and Keith Cameron here have shown that the key drivers of nitrification in our urine patches under fertiliser are ammonia bacteria, AOB, ammonia oxidizing bacteria. Traditionally, it was a two-step process where we had ammonia oxidizers, then nitrite oxidizers that take NO2 minus to nitrate. More recently, bacteria have been identified which can do the whole process, complete ammonia oxidation, COMAMOX. But from the work that's been done, it still looks like the ammonia oxidizing bacteria are our dominant organisms producing nitrous oxide from nitrification. So where does that nitrous oxide come from during nitrification? Well, it actually occurs because some of these nitrifiers actually carry denitrifying genes, which we'll talk about in a moment. But we said the process needs oxygen, but we know that when we get irrigation, rainfall, respiration going on in the soil, oxygen concentrations can become low. So these nitrifiers find a way of surviving by actually reducing some of the product that they're making, nitrite, taking it back to nitric oxide, and then taking it through to nitrous oxide here. This process called nitrifier denitrification. It's very hard to measure the fraction of nitrifier denitrification going on in the soil. We can use stable isotopes in the lab, label the oxygen atom with 18O and do all sorts of things and prove that the process is happening, but we don't actually know the relative contribution of that. But in terms of inhibiting N2O, what we really want to be doing is blocking this process right here so that we don't get the potential for nitrous oxide to form. The dominant process for making N2O in our pasture ecosystems is denitrification. So the nitrate has been formed by nitrification. It now gets reduced back to nitrite, to nitric oxide, to nitrous oxide here. And if it went to completion and formed dinitrogen N2, it would be brilliant. That would be environmentally benign. 78% of the air we're breathing now is this N2 molecule. So another way to think about mitigation, if we can't control nitrification, would be to try and enhance this conversion of N2O to N2. The difference here, apart from the actual process in terms of requirements for the microbes doing this, and again it's predominantly bacteria in the soil, is that this is an anaerobic process. So it needs zero oxygen to kick off, and if oxygen gets into the system, the process will eventually stop, but the most sensitive part to oxygen is this conversion of N2O to N2. So trying to actually stop N2O emissions from denitrification is very hard. The best thing to do would be to stop nitrate forming, and to do that, we really want to stop the initial nitrification process. So where are our nitrogen inputs coming from? This comes from some guidelines in the IPCC. We've got the key players here are synthetic fertilizers, maybe some organic N fertilizers if we were in Europe perhaps, and urine and dung from grazing animals. This nitrogen goes down to our land terrestrial farming systems here. We might also be getting some ammonia volatilization coming off these N sources as they're applied or as they're stored. That ammonia can be deposited back onto the landscape as well. And we end up with two components to our N2O emissions. We have direct emissions here, which are coming directly off the site of application, where the fertilizer or the urine or the dung lands on the pasture. But we have these indirect emissions coming off where the ammonia gets deposited or where nitrate is formed in the landscape or our waterways, where denitrification can also happen. So the dominant input there, besides being those different forms, fertiliser, urine, dung, is urea. So we can think of that as we all recognise the fertiliser pools here, or the nitrogen going in the urine when our ruminants excrete. So maybe 70 or 90% of the urinary N is in the form of urea. So it's just the same compound, it's in a different form, but that's the last we see of it. We can't see this moving through the landscape. So how much do we lose as N2O? We can go through, as Laura Buckthorpe did here with a study, we can put on urine, springtime, autumn, no urine. We can measure N2O over here almost 400 days. And what she found was that we've got less than 1% of the total N applied. If we went to the IPCC guidelines, they would say that we'd lose about 2% of the N applied in our excreta or our fertiliser. And our rule of thumb as researchers is that we'll lose approximately 1%. If we had compacted soils under irrigation in summer where it's warmer, microbial activity is really thriving, Steve's measured 4 or 6% of our N going off as N2O. So why do we bother? It's only 1%. Well, first it's a greenhouse gas, and New Zealand signed the Kyoto Protocol and the Paris Agreement, so we're obliged to create an inventory of our N2O emissions, greenhouse gas emissions, and then take responsibility for those. So we have to know what they are. It's also an ozone depleting gas. It's got a very long lifetime in the atmosphere, about 100 years. It goes to the stratosphere, wavelengths of sunlight, break that down, and the breakdown products go on to react with the ozone and remove the ozone from the stratosphere. So it's the dominant anthropogenic ozone depleting substance at the moment, now that the Montreal Protocol has well and truly come into effect. The other reason is that denitrification is the dominant process by which we are getting N2O emitted from our soils. And while we may be losing 1% as N2O, we're also losing about 20-25% of our nitrogen as N2. So both those gases are coming off simultaneously. And if you start saying to farmers, well, 25% of that nitrogen that you've just put on as urea fertiliser is potentially going to come off as N2, that starts to become a financial reality. I think this morning, as of 4 a.m. on the Ravensdown website, urea is about $1,300 per tonne, and it's probably going to go up with what's happening in the Middle East. So there's a financial cost to this, not just an environmental impact. Now that, let's say it's 1% there, we talk about 1% of the nitrogen applied coming off as N2O. We can talk about that as an emission factor. So 1% of that fertiliser came off, and that's the emission factor. In New Zealand, and it's pretty horrifying to see when it started, about 1998, because I can remember the first meetings in Wellington, when what's it called then, Ministry for the Environment, we're trying to work out what we should do to get an inventory going. And it quickly became apparent that things like urine patches and fertiliser were the key sources of N2O. But since that time, the inventory's developed. Now, if we know nothing, we have to use the IPCC default emission factors. So emission factor is abbreviated to EF here. EF3 is what's coming off the pasture, range or paddock. So in our case, it's the pasture. The IPCC default is 2% of the total N excreted onto that area coming off as N2O. And in New Zealand, that's initially revised down to 1% in 1998 after a series of experiments around the country. Further work goes on, so MPI over the years has funded more work to refine the inventory. And this by default is mitigating the inventory by bringing down our total emissions. Now, initially you can be skeptical and just say, well, this is just rearranging the deck chairs, we're not really changing what's going on. And I can see that point of view, but I would also argue quite strongly that we're actually getting a better number on what the accurate emissions are. So, and therefore we're also knowing where we can target mitigation. So this EF3 has gone down, now it stays at 1% for urine, which is predominantly urea, but we know that dung has got a different composition of nitrogen, mainly organic, and it emits much less N2O. So that has a lower emission factor. So that was 2011. A big development, 2020, some of the work by Tony van der Weerden and others, they looked at the slope of where this urine in particular is being deposited. They looked at low slopes, medium slopes, and a low slope was anything less than 12 degrees in terms of slope. And they could refine the EF3 under urine there and for cattle, deer and sheep, and depending on the slope you can see the emission factor there is much lower. That's predominantly because that urine runs down the slope and your effective deposition rate is much lower. The lower the end rate, the lower your N2O emissions. Work also looked at trying to improve our estimates of N2O emissions from nitrogen fertilizers, urea fertilizer, and this one at the bottom here, N2O emissions from groundwater, estuaries and rivers, which again the IPCC has quite a high number on, but even this number here is probably too high. So they're the emission factors. The other things that have been studied over the years here in New Zealand, and I should say that New Zealand is world leading in trying to do this. A lot of other countries are now replicating some of this work to look at their own inventories and industries. The IPCC default said that 30% of all the nitrate produced will be leached. And several studies have shown, using modelling, measurement and catchments, that is an overestimate. And we've gone down to 7% here in 2003, and for cropland it's got its own value here. The IPCC state that when we put down urea fertilizer or we have urine patches, 20% of that nitrogen will go off as ammonia being volatilized into the atmosphere. So work from an earlier colleague, Rob Sherlock, showed that that's actually 10% when he did a meta-analysis of some of the work here in New Zealand. So that was adjusted there. We've got other values here. In New Zealand, we've gone back and looked at the amount of N that's excreted into manure management systems. So we can take IPCC default values, but we can also actually go out and measure on farm and see what's happening in terms of manure storage. We've revisited the N content of pasture. So while there is a good, really good historic database in New Zealand, which by chance came from all the work that was done on animal production over the years, how do we feed animals better, the use of nitrogen fertilizers and things within New Zealand. So since 1990, urea use has gone up 550, 600%. Our N contents might have changed on average in pasture. So that's all been revisited. How much N is being excreted in the urine versus the dung, again, has all been revisited. So all that work means that we've now got a decrease in New Zealand's N2O emissions. So with New Zealand's N2O inventory, or any country's inventory, you have to report from a base year. So that's 1990. And if you go and revise and put in a new emission factor, a new fraction factor like frac leach, you have to go back and recalculate your inventory from 1990. So this assumes there is data to do that, but usually that's the case. So in 2007, this is what our agricultural NTO emissions were here. And since 1990, they've gone from about 32 gigatons of N2O through to about 40. And then with each development, so we've changed the fraction of gas coming off as ammonia, recalculated the inventory, we see that our total emissions drop. When the emission factor was decreased for dung, the total N2O emissions drop because there is less N2O now coming off the dung component of the N excreted. And this whole inventory for grazing animals is driven by the amount of N being excreted. So you have to know all your animal numbers, but also how much N each animal is excreting. That's all multiplied out to get the total amount of N excreted, and then these emission factors operate on those total amounts. The urea fertilizer has gone up 500–600% since 1990. You change the emission factor for that, and you also see another reduction in the inventory. Add in the lower emission factors for where those animals are on sloping country that have got lower emission factors, and the inventory drops again. But it's not all a downward trend. If that science does show that emissions have gone up, MPI to their credit have to, of course, increase the inventory. So here they were looking at organic soils and what is classified as an organic soil, and they actually found when they looked at the New Zealand soils database, etc., that we've actually got an increase on what would be classified as an organic soil. So the inventory goes back up. So this has got nothing to do with finding a technical challenge for N2O mitigation per se, but it's getting the right numbers to understand where N2O is coming from and how much. Now, I mentioned the slope there, and we've got three columns here. The first one is our emissions based on slope, steep, medium and low, based on the land area there. Then we've got, sorry, that's the land area. We've got 40% steep, 37 medium, 21% low. Then we've got how much N is being excreted in these areas. So steep, medium and low. And then finally, we've got the direct N2O emissions. 80% of our N2O emissions are coming off our low slope land. So logically, this would be a key place to target mitigation. We can get vehicles on there to spray or do whatever. We could cultivate, put different plants in, if that was what was the desired aim. It's where we're using fertilizers predominantly in terms of nitrogen fertilizer. So this should be the target zone for mitigation. 2 months, okay. So where to start, where to mitigate? So I mentioned we've got to block nitrification, and I'll mention a couple of options that Steve will talk about that in more detail. If we can block nitrification there, then those downstream effects, N2O, nitrate leaching, denitrification, are minimised. We can start by using a urease inhibitor to try and slow down ammonia volatilisation, try and give that plant longer to take up the ammonia as it comes on stream. Or we can apply nitrification inhibitors. DCD that was previously on the market was a good example of how a nitrification inhibitor can work. It could be applied alone, like DCD was, sprayed onto the pasture. Might be applied with fertilizer, which is a good way of targeting the fertilizer emissions, maybe not the urine emissions. Or we might look at doing this with plant-associated pathways, things like root exudate chemicals and something termed biological nitrification inhibition. We might also use a different type of fertilizer. On the market, we've got slow release fertilizers. The one that I know of is still a urea compound, urea fertilizer, but it's coated with coated with polymers to make it a slow release fertilizer. We might also look at organic fertilizers, and we don't have much research looking at how these might be affecting things like N2O emissions. The other thing to do is try and push this nitrous oxide reduction to dinitrogen. And what we need to do that is get a better understanding of the enzymes that are doing that and their activity. NOSZ1, NOSZ2, they're affected by pH, carbon supply, who's in the microbial community. Some microbes carry these genes, some don't. And some work in Norway at the moment has looked at places where denitrification will be happening. They've identified things like slurry storage, identified microbes there, and they've managed to back inoculate the soil, if you like, to increase the population of enzymes with active NOSZ, and they're seeing lower N2O emissions. So I know there's some interest in New Zealand and a bit of work going on in that too, but it comes back to activating the microbial community that are carrying and using NOSZ. We can do other things to reduce denitrification. We can encourage aeration. Maybe we can subsoil to get more oxygen into the system, shut down denitrification. But we've got to avoid nitrate leaching if we do that. So we might use some winter active grasses. Other things we can do protect the soil structure to stop denitrification. So that's a quick overview. The list of possibilities is far from complete, but Steve is now going to take over and give us some examples of what the ideal mitigation tool might be.
Thanks very much, Tim. It's a great pleasure to be back here. I'm not an ex-graduate, I'm a graduate. So I'm going to talk a bit more about the solutions. Tim gave a great introduction to a lot of the detail. The process is really important, but also sort of pointing to where the intervention points are coming. So first off, I need to think anyway, about what is a good mitigation. It needs to be effective and quantifiable. First of all, it's got to reduce emissions, and it could be both direct and indirect, or just direct, but the key thing is that it's reducing emissions. The other thing, it needs to fit within the farm system. So it needs to be practical and scalable. So there's no point if it's just working on a small part of the land. It's not going to amount to so much. It needs to be economically viable. So farmers aren't going to use it unless it is viable. I put economically viable, profitable up there as well, because some of the mitigations may mean you become less productive in terms of production, but it doesn't necessarily mean you're less profitable. And so it's, I think that's important to recognise. Improves nitrogen use efficiency. So through Tim's talk there, that we want to reduce the amount of losses from the nitrogen cycle. Remember, nitrogen is critical and the most important nutrient in growing anything in terms of crops and plants. So the more that we can keep within the farm boundaries, the better. But at the same time, there could be some trade-offs. And the biggest issue is probably, is it going to increase methane emissions? Because that's the big problem basically for our pastoral systems. It's way bigger than the nitrous oxide problem. But the other one is water quality as well. So obviously that's pretty important to a lot of us who drink water around here, for example. That's just another slide. As Tim has sort of pointed out, nitrification is an obvious place to focus on, and if you don't get that, the denitrification part will go into
a wee bit more there. I'm going to talk about one particular mitigation that's been around for the last sort of decade. A lot of work's been going on plantain. So this is an example of a trial conducted by my colleagues, and it's looking at different proportions of plantain and urine applied to those and measuring the nitrous oxide emissions. So big takeaway from that study was that there was a big reduction in nitrous oxide emissions. So pretty good, eh? So we can stop there? No, we don't do that. And we're scientists. We want to know what's going on because we know that nitrous oxide emissions are notoriously variable. As Tim has told you, shown you, it's a very complex set of processes that lead to nitrous oxide emissions. So we need to make sure that it works under many different conditions. The table that Tim produced, where we looked at different reducing the emission factors in New Zealand, huge amount of effort went into that. And as Tim pointed out, one of the big reductions comes when you separate out the slopes and from the flats. So this is showing some of the tools we use to do some of this work. We do some work in the glasshouse, but we also work out in lysimeters out there. And that allows us to start looking at what are the effects of different soils, different cultivars, different climates. We want to understand what is causing the variability. So I'm going to carry on. Do we understand the mechanisms? Say we probably don't yet, but this is just an example of the variability that we sort of find. And this is showing the effect of different soil types and different proportions of plantain there. On the right-hand side, you can see that the line there going through the data, that relates to the allophonic soil. So we're seeing the nice reductions. That's 50% reduction in some cases, but it's variable depending on the proportion of plantain. But with the clay soil, a lot less, it's a lot less effect, let's say. So it's, when you look at that line, it's not looking good for a clay soil. So that's good. We understand some of the implications there in terms of variability. It's going to work on some soils better than others. It's also very dependent on the cultivars, and that's been quite an important discovery, really. So there's one particular cultivar that's had a lot of work done on that is showing consistent reductions in emissions, whereas a lot of the others, maybe older ones, different cultivars, aren't showing that. So the soil type I just pointed to, there's also regional differences in emissions. So we can start quantifying some of those effects, but we still need to understand the mechanisms better. I've just mentioned longevity here because one of the initial issues raised by farmers was that they would plant plantain into their swards and they wouldn't last. They were expecting them to last a lot longer. But farmers being farmers, they've worked out how to keep proportions of plantain in their swards. So they might oversow when they're applying some fertilizer at some period. And at the same time, there's a lot of work been going on to understand how to manage. So going alongside that, there's a lot of extension work. So people like dairyans have put a lot of effort into helping farmers grow plantation. So the nitrous oxide reduction, if you're on the right soil and so on, that's great. But there are other benefits. So reduced risk of and leaching loss, and that's where the initial focus on plantain came from. So seeing effects on reduced leaching when you have plantain in the system, and the mechanism there is probably greater plant and uptake compared to ryegrass. So the comparison I'm making there is with the traditional pasture ryegrass. system. But another thing is that when animals have a diet of plantain, they also have lower nitrogen concentration in the urine, and they urinate more volume. So that's actually quite an important thing as well, because it ends up spreading the amount of nitrogen more thinly across the paddock. So more urinations at lower concentration, it reduces the risk by having less of a load at any one place. And there are other benefits that people have talked about, sort of mineral composition of the pasture as well. But it also means that it's different from what you're currently managing, so you need to understand a bit about how to do that. So here are some of the science gaps. The microbiology. So Tim was explaining that these processes are mainly through enzymes, and so that's the microbiology associated with that. And we don't have such a great understanding of where that's happening, why it's happening, why the changes are happening there, the expression of the enzymes, and yeah. So we want to understand that more. There's been quite a bit of work looking at secondary metabolites, for example, trying to understand if they're one of the reasons for doing it. There's looking at exudates quite closely in terms of how they're affecting nitrification. There are other things, as already pointed out, the climate, soil being important. We want to understand that better so that we can inform farmers as to the best way, the options for them. We don't perhaps understand how much an interaction with clover might be an issue or not, but that's something that we should be doing, probably on the lower end of the list, but that's the sort of thing that can be easily done. Just going back to the reason sort of giving this presentation, for all of this work, Tim has sort of taken us through the range of it as well, but we need the background fundamental research to understand, and some of this work around the microbiology going on, understanding exudates and so on, it needs some new fundamental research. It needs to be multidisciplinary. It needs to, I'm going to say cross-institute universities too. We need to capitalise on the skills we've got in the country. So I'm going to touch on some of the other mitigations. Some have been around a bit longer. So this is a one where you take the animals off the pasture during winter, and so that's the period when you're most likely to have wetter soils, your compacted soils, and so on. As Tim sort of highlighted, those are good conditions for denitrification and losses into O's. Also, potentially periods when you get a lot of nitrate leaching. So here are some results from across the country from some of my colleagues. And in each case, using something like standoff housing, you get a reduction in nitrate leaching losses. So less nitrogen's going onto the paddocks at times when it's likely to leach, and you get less nitrous oxide emissions for similar sort of reasons when those wet soils tend to be high emitting. So that's a good mitigation, but it is potentially an expensive one. So there is also the potential for pollution swapping issues in this case. There could be ammonia and methane losses, particularly if you're storing manures. And another thing that can potentially happen, an unintended consequence, is that you've got to keep your banker happy. So how do you do that? I'll get some more cows and make some more milk. So just got to be aware that yeah, it's the whole system that we need to be thinking about. Tim touched on this, the urea hydrolysis, so the urease inhibitors. The Climate Change Commission, I think a few reports back, recommended that all urea should have urease inhibitors, and that would be actually not a bad idea, as long as it wasn't a large cost, because you're guaranteeing some reduction in ammonia losses. Yeah, so in this case, you could they found differences of 45% reduction. So it's a simple and scalable type intervention. Low greenhouse gas emission feeds. So this was a study that was looking at fodder beet and kale. So urine from fodder beet produced less emissions than urine from kale when it was applied to the soil. And gone over that's another trial that looked at the effects of plantain and ryegrass and ryegrass urine in this case. So those were single interventions, but there's also improving the farm system that you've currently got. So just changing some of the management. And I guess I've been interested in this for some time, mainly because I've been working with crops. So tillage is one of the key management going on in those cropping systems. And Tim has sort of highlighted that soil aeration is a key thing that we need to think about because of its impact it has on emissions. And tillage can aerate. Compaction from that same tillage can have the reverse, and it could be a compaction from livestock as well as mechanical is potentially a big problem. On the right hand side, this is some work we did quite a few years ago, but we looked at winter grazing scenarios here in two different studies. One was on a freely draining soil and the other was on a poorly draining soil. And in both cases, we established the forage crop either with no-till or tillage. And then, and it was compared with continuous pasture. And then we simulated grazing. And so the extraction, taking off of the forage. And the key things, well, there's some key things here. So this top line there was on a poorly drained soil. And when you're grazing on a poorly drained soil in the middle of winter, this is what we found, these big emissions. And it was a combination of the compaction, the tillage that established the crop, so breaking up the structure, never recovered through the single crop that went there. And then, yeah, that's why you've got a big difference there between the tilled soil and no-tilled soil, just used to establish crops. So, and these are things that we're talking, trying to teach and work with our cropping farmers to minimise the tillage. But the other big thing there's hardly any emissions from this. It's really freely draining soil, same conditions there. So soil type, just enhancing that. As Tim mentioned, we've looked at improving irrigation management as a potential mitigation. And again, there are benefits here of if you can reduce the amount of irrigation you're putting on, you're retaining a deficit in the soil, it's more aerobic. If you can maintain that for as long as possible, you reduce the risk of N2O emissions and leaching. So, and at the same time, you can do this well-managed precision type systems, especially without impinging on any yield loss, but you get the environmental benefits. Another one there, we've done quite a bit of work on cover crops. If you've got a fallow area that's sitting around during the winter, it's been mineralizing and so on, it increases that risk of both nitrous oxide emissions and leaching. So that's, yeah, avoiding that is a good management practice. I'm not going to talk about the recovering N from residues, except to say in cropping systems, a lot of the nitrogen that goes into the crops comes from the previous residues. So managing that is quite important for systems. This is something I took off the AgriZero website, and just to sort of focus there. One, we've got urease inhibitors already deployed. They're looking at changing bacteria. I'm not sure exactly what it is. Some of these are very secret, but there is work going on inhibitors still. Those are the 3, 4, and the plantain, of course. Those are the 4 things that are being focused on there. I'm going to, Tim mentioned biological nitrification inhibition, BNI. We're thinking this could be quite an important way, as well as chemical inhibitors. Biological inhibitors work the same way. They inhibit the nitrification process. But if we can get the plant to do that, and we can plant across our paddocks, then we've got very scalable type mitigations. And so we're finding BNI in some plantain crops, plantain cultivars, but also there is BNI in a wide range of different crops as well. And so looking at the potential there, and that includes some of the high-performing ryegrasses too. So I'm just sort of winding up now. Some of the other things that are we've touched on there. Partitioning nitrogen in urine and dung, that's one thing that actually happens through the plantain feeding. Novel fertilizers, Tim touched on those, and application technology. So there is a lot of interest in there, and I know Agri-Zero is looking at funding some of that work. I'll just jump to the bottom, improving farm system models. So we've done a lot of work. We've got a very complex system. We've got a farm system, which is also complex. So the better we can get our models to work and tell us what's going to happen, what's likely to happen, the better. So a lot of research should still carry on to help those models. In summary, there is no silver bullet, no single solution, particularly when it comes to the farm systems. We need to keep on targeting where the problems are. So that's the urine patches and excreta. We need to look at various tools across the farm system. We still need to focus on how we can make them economic and viable. And the other thing is we need to be able to measure them. And policy support, well, that might be useful. Yeah. So thank you very much.
Thank you, both of you. That was a wonderful kind of introduction, and you kept on time, so I'm really thankful for that. I have a few questions. You've answered a couple of them, actually. So I'll pose those. You're welcome to come up. Either of you or both of you can answer, and then we'll open it up to the audience. So the first one is around barriers to uptake. Even when strong science exists, adoption can be slow. So what do you see as the key scientific, economic, behavioral, or policy challenges preventing wider implementation?
So for me, I think it's cost. If you've got a mitigation tool on the market, why is the farmer going to use it? If it's going to cost money, what is the farmer going to get back by spending that money? Is more dry matter going to be produced? So therefore more milk in the vat. At the moment, there's no policy which says a farmer must use a mitigation tool. So there's no policy driver. Anything that's going to make it happen at the moment is an economic decision. Part of that may be, they're trying to look at the farm nitrogen budget. And if you've got a tool that also reduces nitrate leaching, that may be another reason why they want to look at using a nitrification inhibitor. So there's a couple of reasons around there, but it's still going to come down to cost. They're going to look at their farm model. If I can reduce nitrate leaching, can I increase stock numbers or stay farming where I am, etc. So,
yeah, what he said, and yeah, I guess it's showing that the benefits of keeping that nitrogen in your system. So a lot of those mitigations could maintain the nitrogen, and that's what we're trying to do. We're trying to stop the gaseous emissions, but at least the nitrous oxide emissions. So there would be a benefit there. I do think that we do need a bit of a stick as well. Yeah, to get some of these things introduced, I would have liked to have seen the urease inhibitor suggestion mandated. I don't know what that there is. Someone from Ravens down here at Balance maybe, but yeah, if it isn't a big cost and done on scale, that's the other thing. It'd be nice to see something that like that intervention.
I mean, the stick might come from the market too. So you've got to sell your product. And the market may say we want clean green products. So maybe it's an indirect stick, not directly from New Zealand government policy as such.
Okay, I'm going to ask one more question, even though I was given 5 or 6. But and this plays a little bit on your last slide. Looking ahead, what gives you optimism? What emerging research technologies or system changes give you confidence that meaningful reductions in nitrous oxide are achievable for New Zealand agriculture?
I think I am seeing some of these mitigations actually occurring on the farm. So seeing farmers taking to plantain without really knowing exactly what it's going to do for them, but they're driven by multiple drivers in that it could be environmental. The catchment groups are really been important in one way of getting farmers to work together and probably seeing a lot more adoption. So they're sharing their ideas around the mitigation. Yeah, I would love to see some more emphasis on this type of work. I'm not seeing that at the moment from the government signals here. So that's a wee bit concerning. But otherwise, yeah, I mean, we've got fantastic researchers in the country. We've done so much good work that's recognised internationally. So yeah, and we work with people all over the world as well. So I am sort of positive from that aspect. But yeah, I think there's so much more we could do.
I think a key thing is that there's a global market for technologies if you can crack it, and from various possible angles, fertilizer technology, plant technology, and globally the plant technology has been hardly looked at, and everyone's scrambling now to try and understand it. Why does a plant turn on nitrification inhibition? How long does it last for? Despite all the years of looking at agronomy in New Zealand, breeding plants, ryegrass, we don't really know why plants are releasing exudates, what they're releasing, why they're releasing it, how long they do it for. There's a multitude of questions there that we need to find out, for some of these technologies.
Yeah, I should have said, well, we've got great breeders in New Zealand. So if we tell them what we need and how to get it in there, then there's a good chance of getting it scalable and deployable.
Thank you. Open it up to the floor for questions.
Slightly technical question here. Nitrogen fixation through nitrogenase, I understand, anaerobic, I assume that they evolve. What are other transformations of
Where's Phil? Oh, he's hiding. I don't know. I presume it's the evolution of those microbes, but the N2 fixation symbiotic rhizobia, they form that nodule which they keep anaerobic. So the surrounding soil can be aerobic, but they've got their own zone. Whereas denitrifiers, some denitrifiers though will respire oxygen. They will switch to nitrate when it goes anaerobic. So they're not all obligate on just using nitrate, nitrite, nitric oxide. So there's a multitude of microbes there. Leah.
wonder how much of the models that are sold sell in terms of the national also the fact sheet numbers continue. Sheet numbers. Nobody's going to solve itself. But there's something that's been back to the
Yeah, those trends will help explain some decreases and reductions in the slope of that increase in N2O. If we have a drought year and production drops and animals go to the works, that shows up in a dip in that year in the inventory in terms of N2O emissions. And yeah, like you say, we've got a lot of hill country going into pine trees. So depending on the relative number of animals in those areas and the amount of N excretion, that will show up in the inventory. Yeah.
And there's also the feedback from climate change. We know that the underlying
Yeah, and like MPI won't want to know about that, but the inventory runs on animal numbers, fertilizer tonnage, the amount of N that's going into the system. But if climate change is going to change that, then that will and it goes through into the data, then we'll see it in the inventory. Yeah.
Can I just add to that, Leo? We're seeing some more dairy conversions going on in Canterbury. So that's another land use there, going from a lower emission to a higher emission system. Yeah.
Could you give us an idea of the magnitude of the point of these nitrous oxide and consequently policy might go in the future? You guys obviously are doing this
So the relative warming, if we think about CO2 as the base, so a unit of 1, nitrous oxide 273 is its global warming potential over a 100-year period, and methane changes every so often, but I think it's about 27 at the moment. So N2O is potent relative to methane or CO2, of course. The biggest greenhouse gas for New Zealand from its ag system is the methane. So again, big technology market there. If you crack it, you've got South America, everywhere that you could sell something to. So no, we're not in a job forever. At the moment, the relative contribution of nitrous oxide to the New Zealand inventory is approximately 8 or 9% of the greenhouse gas basket. Oh, okay. Watts per metre squared. I couldn't give you that off the top of my head, but yeah.
10 times.
Yeah. So it depends on its relative. I mean, it's increasing in the atmosphere continuously, hasn't gone down, but anthropogenic warming, don't quote me, it's a couple of watts per metre squared. So it's a small fraction of that. CO2 is by far the biggest globally. And if we looked at the Australian greenhouse gas inventory, they're not really worried about methane and nitrous oxide, well, they're not worried about greenhouse gas. But if they were, they're worried about CO2 because of all their fossil fuel emissions from energy production, coal-fired power stations. Their agricultural contribution is much lower. And you can see many other countries are like Australia. Countries like New Zealand would be maybe Ireland with its strong agricultural base, or you go to South America, Brazil, Argentina, Uruguay with higher cattle numbers and things. Yeah, but globally CO2 is still the big one. But N2O does have that stratospheric ozone issue with it as well.
Just the other thing you would know was that nitrous oxide is a long-term gas like CO2. The methane is the shorter.
We have time for one more question.
Over here.
Thanks. done a much better job over the past 20+ years of getting an accurate picture of our emission. But has anything happened over that amount of time change our emissions in terms of nitrous oxide? So those fluctuations in trends over time, is that just the price of dairy versus the price of urea fertilizer, or is there any practices or things that have come online that have actually helped increase emissions?
There's been changes in animal numbers. So sheep have gone down, but the void has been filled by cattle numbers. The intensity of the production or the efficiency of that production has probably increased, which has perhaps slowed how steeply that slope has gone up. In terms of the inventory, when DCD was on the market, that was plugged into the inventory. That could be allowed for. If you could say how many dairy cattle or even sheep were under that management strategy, you can plug that into the inventory and allow for that technology. Urease inhibitors are in there. And then, like I mentioned before, annual variation goes in there, drought and things like that. But other than that, there are no real changes that are going on per se that I can think of that are dramatic.
Well, I guess it might be some of those like the herd homes or that type of standoff pads. So there are changes in the farm systems and they will be picked up in some of the model, but I can't tell you. Yeah, but I'm sure there are things that are being picked up. Some of the winter grazing has sort of changed in the way they do that, and yeah. Yeah. So no, but I guess it's the models that they could change it, but I don't know what. Yeah.
Well, join me in thanking the two speakers. Thank you. Thank you very much. And please join us outside for drinks and coffee.